In this video we're gonna look more at the area under the normal distribution curve and how to use the percentage in different region of the normal distribution curve to analyze some situations and answer some questions. So consider a consumer report survey in which participants were asked how long they owned their last TV set before they replaced it. So the variable of interest in this survey is the replacement time for TV sets. Based on the survey, the distribution of replacement times has a mean of about 8.2 years, which we denote as mu. Usually mean is the overpopulation is given the Greek letter mu. And the standard deviation of the distribution is about 1.1 years. And this is denoted by the Greek letter sigma. So this is makes sense that this is a normal distribution because probably most sets would be replaced around the mean time of 8.2 years, and an equal number would be replaced before and after the mean, and not many would be replaced right away, and not many would be replaced very far in the future. Not many people hang on to their TV for 20 years. So let's look at a picture that goes with this situation. As I said, normal distribution for the replacement times for TV is a mean of 8.2 years. So the mean is the central line right here in the middle of the normal distribution. And the standard deviation of 1.1 years. So the standard deviation, denoted by the Greek letter sigma, is the region. You can look at the region of one standard deviation away from the mean. So if you subtract 1.1 from the mean, or you add 1.1 from the mean, then you get a region that's within one standard deviation of the mean. Okay, now this is an important region because 68 with the normal distribution curve, with this particular curve, we know as a fact that 68% of the data fall within one standard deviation of the mean. So if you take the mean and you subtract the deviation and you add the deviation within that region, within that area, we know that 68% of the data is included there. Now we also know that if you look 2 standard deviation away from the mean, so that means that you take the value of the mean and you subtract 2 times the value of the standard deviation, and then you add 2 times the value of the standard deviation to the mean, then in that region 95% of the values are included. And if you go even further, 3 standard deviation on either side of the mean, then 99.7% of the values are included in there. Okay, so this is called a 68, 95, 99.7 rule. Sometimes it's called a 98% rule. And it gives precise guidelines for the percentage of data values that lie within 1, 2, and 3 standard deviation of the mean for any normal distribution. So how this is useful is that you are able to find the percentage or the proportion of the data for different scenario. It's also very helpful because it tells you if you have an unusual value or not. If you have something that falls outside 3 standard deviations, you know that you're falling outside 99.7% of the data, then that's a very unusual occurrence. So that's another way to analyze the data. You can tell whether something is unusual or not compared to the rest of the data. Here's an example of how we can use that rule. Let's look at SAT scores. The tests that make up verbal and mathematics SAT are designed so that their scores are normally distributed with a mean of 500 and a standard deviation of 100. Now it says interpret this statement. Okay, so let's do that. So we can use this figure with the 68, 95, 99.7% rule to see what that means. Okay, so the SAT scores have a mean of 500, so that means that people on average score 500 on each of those portions. Now when it says that they have a standard deviation of 100, if we subtract 100 and add 100 to the mean, we get this region from 400 to 600 for the score between 400 and 600. That's within one standard deviation of the mean. So we can conclude using that rule that 68% of the students will score in that region. 68% of the students will score between 400 and 600 on one of the portions of the SAT test, because that test is designed to be normally distributed. Now if we look within 2 standard deviation of the mean, that means we subtract 200, add 200, we get this region between 300 and 700 for the score. And using that rule, we know that 95% of the students will score between 300 and 700. And if we look 3 standard deviation on either side, we can conclude that 99.7% of the students score between 200 and 800 on the SATs.